Hi everyone, welcome to your lecture on genetic algorithms in computational economics. Today we're going to be going all the way from basic biological principles that inspire these algorithms all the way to practical implementations in economic modeling. We'll be able to see how concepts such as natural selection, genetic crossover, and mutation can be used to solve problems that traditional optimization methods often struggle with. Let's begin with a fundamental concept. Genetic algorithms are nature inspired optimization techniques that are based on evolutionary principles. If you think about it, nature has always been solving these optimization problems for millions of years. How do birds develop the wing structure needed to efficiently fly? How can predators evolve the ideal hunting strategies? And the answer to that is evolution, which is this continuous improvement through selection, reproduction, and variation. So, this first bullet point, selection of the fittest, draws on the idea that we have something called natural selection. In nature, we observe three main processes. First is selection of the fittest, which means that organisms with advantageous traits are more likely to survive and reproduce. Secondly, we have reproduction through crossover. So, offspring are inheriting characteristics from both of their parents, and this allows for the creation of new combinations of traits. And finally, we have random mutations. So these are occasional random changes that introduce entirely new possibilities into the population. And this third point is really important that genetic algorithms evolve solutions to complex optimization problems over many generations. So, unlike traditional optimization methods, that might get stuck in a local minima, genetic algorithms are able to maintain a population of diverse solutions and be continuously exploring the solution space. This makes them especially helpful for economic problems where the optimization landscape might be super complex and multimodal or just not that well understood. Okay, let's break down the 5 essential components that make genetic algorithms work. First, we have the population. This is our collection of potential solutions. So, in biological terms, this would be all of the organisms, say, in a species. In our computational context, each individual in the population represents a different approach to solving our optimization problem. And the size of this population is important because if the population is too small, we might not have enough diversity. But if it's too big, our algorithm might be too computationally expensive. The second component of genetic algorithms is the fitness function, which measures solution quality. This is analogous to environmental pressure in the nature. So, just as environmental factors will determine whether animals are more or less likely to survive, the fitness function will determine which solutions are more likely to be selected for reproduction. It's really important that you carefully design this fitness function to make sure that it captures what we really want to optimize. Third, selection. Selection means choosing parents for reproduction. In nature, again, this might involve competition for mates or resources. And in our algorithm, we will use various selection schemes. Some give every solution an equal chance, others bias toward higher fitness individuals. And overall, the selection pressure affects how quickly the algorithm converges and whether it maintains diversity. Fourth, crossover combines parent solutions to create offspring. In this stage, we're not just copying existing solutions, but we're actually creating new combinations that might be better than either parent. And different crossover methods exist for different types of problems, so we'll explore a few of those today. And finally, we have mutation, which introduces random changes to maintain diversity and explore new areas of the solution space. Without this mutation, our population might converge too quickly, resulting in suboptimal solutions. So, mutation makes sure that we don't lose that ability to discover entirely new approaches. So, we start with initializing the population. We'll create an initial set of n randomly generated solutions. It's important to note that we don't assume that we know where good solutions might be, so we start with a diverse random set. And this random initialization helps make sure that we're not biasing our search toward any specific region of the solution space. Next, we enter the main reproduction cycle where we create m new solutions. This cycle has 3 steps. First is selection, so we select m parents from our current n solutions to reproduce. And different selection methods, again, will choose these parents differently, some randomly, others based on fitness. And the important takeaway here is that in nature, not everyone gets to reproduce, right? And so the same is true in our algorithm. Next, we have crossover. So we create M children from the M parents. And this usually involves pairing up the selected parents and having each pair produce offspring that combine characteristics from both of the parents. And again, this is where new combinations of solution features are explored. Finally, we have mutation. So we randomly select different parts of the new children to alter. And this step is really important for maintaining genetic diversity and making sure that we can explore new regions of the solution space that might not have been reachable through crossover alone. All right, now we have the survival step. We have n original solutions plus m new children, so that gives us n plus m total solutions. We can only choose n number of individuals to survive to the next generation. So this is really survival of the fittest. We're keeping the best solutions and eliminating the weaker ones. Final step of the genetic algorithm is termination. So we repeat this cycle until we meet some stopping criterion. This might be a fixed number of generations or convergence to a predefined acceptable solution, or simply when the population stops significantly improving. Now, let's talk about why genetic algorithms are especially important in economic contexts. Economics deals with so many complex systems, such as multiple interacting agents, strategic behavior, and emerging phenomena, which are exactly the kinds of problems that evolutionary approaches excel in. So, firstly, we have market behavior. Being able to simulate this is one of the most important application of genetic algorithms. Traditional economic models oftentimes assume that agents have perfect information and make optimal decisions. I'm sure that you have all learned a bit about that in game theory with Dr. Kovanak. But what if we model agents as having limited information and learning over time? Genetic algorithms can simulate how different agents, so firms, consumers, investors, evolve their strategies based on market feedback. For example, firms might evolve pricing strategies in response to competitor actions and consumer responses. The search for Nash equilibrium in competitive environments is another main application. In game theory, again, finding equilibria in complex multiplayer games can be very difficult to model computationally. Genetic algorithms can evolve populations of strategies and observe which combinations end up remaining stable over time. And this is especially valuable when we can't solve directly for our equilibria in an analytical manner. Next is auction design. So, how do you design an auction mechanism that achieves specific economic goals? You want to maximize revenue, make sure that there's fair allocation, minimize bidder collusion. Traditional mechanism design theory provides some answers, but genetic algorithms can explore much more complex auction formats and bidding rules that we could analyze mathematically. Evolutionary economics also represents a broader philosophical approach which views economic systems as continuously evolving rather than being in an equilibrium. And genetic algorithms give us the tools to study how economic agents adapt to these changing environments and how new market structures emerge, and in general, how economic systems can respond to shocks. Now, let's make these concepts a bit more concrete with the classic knapsack problem. This problem is great for understanding genetic algorithms because it's pretty easy to visualize, but it is also computationally rather challenging, in my opinion, to solve optimally. Let's imagine that you are packing for a hiking trip. You've got a backpack with limited weight capacity, and you're faced with several items, each with different weights and values. Maybe you have a heavy tent that's super valuable for shelter, or light snacks that might have a moderate value. And your overall goal is to maximize the total value of items you pack, but without exceeding your weight limit. This is considered a constrained optimization problem. We want to maximize our overall value subject to the weight constraint. What makes it challenging, though, is that it's a discrete combinatorial problem. For each item, we're having to make this binary decision, right? Take it or leave it. So with p items, we have 2 to the p possible outcomes. That's over a million combinations just for 20 items. Let's take a look at this example. Here, we're defining an item class, which encapsulates all of the properties that we need for each potential item in our knapsack. And each item has 4 attributes. Firstly, it has a name. Next, it has a weight. So in this example, it's going to be the physical weight of that object. Next is the value or the benefit we get from it. And importantly, a ratio of value to weight. And this ratio kind of gives us some intuition about which items might be most attractive. So items with a high value to weight ratio is probably going to be more preferable. So let's look at our example items. Notice how the item values differ significantly in their characteristics. I'm just going to run this block of code and see how different the ratios are and the values and the weights for each item. This diversity is what makes the problem challenging and interesting because a simple greedy algorithm that always picks the highest ratio items might not always find the optimal solution because of the weight constraints and discrete item sizes. Now let's move on to creating individual solutions. So the function random knapsack solution with num items as an input generates a single randomly generated solution for a knapsack problem. And this function is very simple but important because for each position, we will randomly choose 0 or 1 with equal probability. And this gives us a completely unbiased starting point. We're not assuming anything about which items might be good or bad. If we had started with solutions that were all similar or biased towards certain items, we might miss out on entire regions of the solution space. And so this random initialization helps make sure that we start with maximum diversity. When we call our function using the length of our items, we get something like this. And this represents a specific packing strategy. So zeros represent leaving the item and 1 represents taking it. So we're going to leave items 1, 3, 5, and 6, and we're going to take items 2, 4, 7, and 8. Each time we call this function, it's going to give us a different solution. And some of the solutions might be really bad. They might exceed the weight limit or just select really low value items. And others might be surprisingly good by chance. And this diversity, again, is exactly what we want in that initial population. Building on our ability to generate single solutions, now we can create an entire population. So this function generate knapsack population using num items and population size as parameters makes us a collection of random solutions that will form our initial generation. So in this example, we've set population size equal to 20, which is relatively small but sufficient for the purposes of this lecture. In practice, population sizes might range, from dozens to thousands or maybe even millions of individuals, depending on the problem's complexity and the computational resources that you have available. The function uses a list comprehension to create population size number of random solutions, and each solution is independent from one another, so there's no relationship between them at this initial stage at least. And this, again, gives us a maximum diversity to start the evolutionary process. For example, let's run this code. Now see, we have the output and we have 20 different binary lists, each representing a different packing strategy. Some of them might be relatively conservative, having mostly zeros, and others might take on a more aggressive approach, having mostly ones. And most will probably be somewhere in between, having relatively equal zeros and ones. However, population size involves a rather significant trade off. So I'd like you to pause this video for a second and try to come up with a potential reason why different population sizes could be better or worse. And I'll give you a hint. It has to do with convergence speed and local minima. Okay, so larger populations maintain more diversity and are less likely to get stuck in local optima, but they require more computational resources. And on the flip side, smaller populations often converge faster, but they might miss good solutions. And so the optimal size depends on problem complexity and also how much available computational resources and how much time you have. The fitness function is one of the most important components of any genetic algorithm because it defines what we're trying to optimize. So let's break down our knapsack fitness function. Our objective is pretty clear. It's to find the best possible solution that maximizes value without exceeding the weight constraint. This requirement to maximize benefit while respecting constraints is very common in economic optimization problems. The fitness calculation involves computing two main metrics. First, we calculate the total weight as the cross product of our decision variables and the weight of each item. The penalty mechanism is very important for handling constraints because if a solution exceeds the weight limit, we return a fitness of 0 rather than the actual value. And that's a pretty harsh penalty constraint, but this approach strongly discourages the algorithm from considering infeasible solutions. So these are equations for the total weight and total value for the items in our knapsack. Looking at our code, we can see that this is implemented in that for each item position, if the solution chooses that item, so the choice equals 1, then we add its weight and its value to our totals. If the choice is 0, we add nothing because 0 times anything is a 0, right? So I'm going to run this little block of code. So in this case, we have a valid fitness value of 30. If we had an invalid solution, say we had a total weight of 1,000, then it would receive a fitness score of 0 because it's invalid despite having higher theoretical value, because again, it's not feasible. Now, this is a pretty common penalty approach in constrained optimization problems. There are alternative approaches that might use softer penalties or repair mechanisms, but with problems that have clear constraint boundaries, hard penalties are oftentimes what is used. This slide introduces one of the most important concepts in genetic algorithms, which is reproduction. And that's how we generate new solutions by combining characteristics of existing solutions, which mimics how biological organisms pass genetic material to their offspring. Reproduction involves creating new solutions or children using parts of current solutions or parents in the population. And we're not just copying solutions, we're creating new combinations that didn't exist in the original population. And so the idea is that we're exploring that solution space more effectively than randomly just searching while building on the success of good existing solutions. The components of reproduction include selection, crossover, and mutation. These work together to balance exploitation of known good solutions with the exploration of new possibilities. That's always something that we're trying to balance is exploration versus exploitation. Selection makes sure that better solutions have more impact on future generations, and then crossover makes new combinations of successful characteristics. And finally, mutation maintains a diversity and prevents premature convergence. But I want you to take a second and think about what might happen if we didn't have reproduction. Without reproduction, our algorithm would be limited to the solutions in that initial population. And since those were randomly generated, the probability of finding an optimal solution would be extremely low. Now, the algorithm would eventually converge to the best of these initial solutions, but this would almost certainly be far from the optimal solution. So, again, reproduction is essential to genetic algorithms because it allows us to explore the potential solution space and find that optimal solution. All right, selection is the first step in reproduction, which determines which solutions get to become parents for the next generation. And this mirrors natural selection in nature, where organisms with favorable traits are more likely to reproduce. There are different types of selection methods. Different selection methods balance this trade off between exploration and exploitation. We have multiple recombination, and the main idea with this is that new solutions are created by combining parts of parents to create potentially better solutions that didn't initially exist. Let's start with the simplest selection method, which is roulette selection. In this selection method, each solution in the population has an equal probability of being selected as a parent, regardless of its fitness. And this is essentially a random selection. We randomly choose two solutions from the population to serve as parents, and every solution has the same chance of being chosen. So, from our population of 20 solutions, we randomly select two right here without replacement from the population. So, let's run that code. Some advantages of roulette selection include that it's very simple and it also maintains a maximum diversity. So, even poor solutions have a chance to contribute to the next generation. And this can be especially valuable when we're not sure that our fitness function perfectly captures solution quality, or when poor solutions might contain useful characteristics. However, there are also significant disadvantages, including that there's no selection pressure toward better solutions. Good and bad solutions are equally likely to reproduce, which means that the algorithm relies entirely on crossover and mutation to support solution quality, and this can also lead to very slow convergence. Weighted roulette selection addresses the main weakness of the basic roulette selection by giving better solutions higher selection probabilities. And this creates that selection pressure toward higher fitness solutions while also maintaining some diversity. So, higher fitness increases selection probability proportionally. Say that we have solution A that's twice the fitness of solution B, then solution A is twice as likely to be selected. But there's an issue that arises when some solutions have negative or zero fitness values. And so our knapsack solutions that exceed the weight limit get a fitness of zero. And in other types of problems, we might even have negative fitness values. So we can handle this through data transformation by subtracting the minimum fitness from all the fitness values to make sure that all of the weights are non-negative. The code here just shows this. First, we're going to calculate for all the solutions in the population, and then we'll create selection weights by subtracting the minimum fitness from each fitness value. And then again, this random.choices uses weights to select parents. So solutions with higher weights are more likely to be chosen, but there is still a bit of randomness involved. So let's run that, see what our output is. And there are obviously benefits of this weighted selection, such as faster convergence toward good solutions compared to that basic roulette selection. And poor solutions still might have a small chance of being selected, which can help maintain our genetic diversity. But there are potential issues like the probability that one exceptionally good solution dominates the entire selection process is a possibility, which would reduce the overall diversity. And also, the method can be sensitive to the overall range of our fitness values in the population. Ranked roulette selection takes a different approach to addressing the issues with weighted selection. So instead of using raw fitness values, it ranks solutions by fitness and bases selection probability on rank rather than absolute fitness values. So, how does this process work? First, we're going to sort all of our solutions by their fitness values and then assign ranks 0 to n minus 1. So, 0 would be the worst and n minus 1 is the best. And this selection probability is then based on these ranks, so not those original fitness values. So, let's run that. This method reduces the effect of fitness magnitude differences. So if one solution has a fitness of 1,000 and another has a fitness of 999, the weighted selection would treat them as very similar. But if one has fitness of 1,000 and another has a fitness of 10, the weighted selection method that we used before might give the first solution 100 times more selection probability. But in ranked roulette selection, both scenarios are more evenly considered. So it only cares about that relative ordering, not the absolute differences. The trade off, however, is that the ranked selection might be less aggressive in exploiting the very best solutions, which could potentially lead to slower convergence in some cases. Next, we have the parent selection strategy, which allows us to switch between different selections dynamically. This is a very valuable selection strategy for both experimentation and for adapting algorithm behavior during our runtime. So, Python dictionaries provide a clean way to implement strategy pattern functionality, and we're able to create a dictionary where the keys are method names and values are function references. However, the keys must be unique and immutable, so strings are a great example. And also, all of the functions need to have the same input parameters. And this constraint makes sure that we can swap methods without changing the calling code. So this is just an example of what our selection code might look like. All right, I'm going to end this video here. And if you have any questions or comments, feel free to reach out to me and enjoy the rest of your day.